back at it again today. Let's see. Just need to make a quick adjustment here. Just set that to 0. Okay, there we go. Just need to take care of a few things before I get started today. It's been a kind of an overwhelming first couple days back from a 2-week break in this journey here. So just trying to get my head around projects and stuff. And yesterday I just got a little distracted into way too many tiny little problems like the one I'm trying to fix today as I start. So bear with me for a moment. Today we're going to start on the linear regression in Python, and that's going to be a real Python tutorial. And just trying to get that link up now. And there should be a link in the description. And but I will add it to the chat as well. Just bear with me for one moment here. Yeah, that did pop up. I don't really want that to happen, but that's okay. There we go. Okay, and yeah, so we'll be working through this, or I'll be working through this. If you want to follow along, feel free to. But yeah, you can chat along with me and, ask some questions about some of the things here. If you're a beginner, if you've never learned about linear regression, this might be a good time to ask some questions. That's interesting. Okay. And let me see. So returning from break, on break is going to be if hotkey is pressed. Right, I got it. Okay, that was the problem. I'm just trying to figure out which triggers should happen. There we go. Transitioning from there. Yeah. Just trying to figure this out here. Okay, I think that does it. I might do a little test here. Yeah, I think that's what I want to do. I'm just gonna delete that hotkey because maybe it just disappeared anyway. Yeah, it did. Okay. Feel free to chat in the chat box there. Before I get started, I think what I want to do is review the first couple days here, and oh gosh, maybe I might need to do a speed test now because the internet seems slow. Let's see what's going on with that. My system seems good. It seems to be handling the computation and caching. Download speed seems good. Let's see about the upload speed. Let's see. Seems good. Seems really good. So yeah, let me edit this in. So going to go through new project for real Python. I'm gonna do that. So I'll get to that in a moment. Let's see. Going back over what I've done in the previous 2 days. Kind of started working on that data modeling project for with the book The Well-Grounded Data Analyst, and didn't start the project. So we read up to the start of the project and just didn't start the project. The thing I want to check for is whether or not metrics uses the same thing here, because when I do this tomorrow, this might be an extension of the second project, and if that's true, then I might have to bump that. And then I would need to do some editing of my thing. So I have a bit of a dilemma here. I want to, let me get back over, come back over here. There we go. So I want to be able to keep my schedule as kind of flexible as possible, but I also want to have a focus for the day. And so the problem is that it really helps to have thumbnails for the live streams to grab attention and kind of give an extremely broad overview of like what I'm going to be covering in the stream. And that helps people if they want to like decide if they want to watch. And having those up front is really helpful, right, for the stream, rather than going back after the fact and then creating it for the replay. So what I did this week is on Sunday, I created all my thumbnails for Monday through Friday, and I set up all the streams. Great. Problem is that what happens if something runs long, which it did, and I don't want to feel rushed to get something done, especially in this phase when we're trying to, like this first week of this build projects thing, where I'm just trying to get into a mode, right, of thinking about data problems again and how to solve them. Everything that I know. So, because like one thing that I was thinking about, was stuck out to me on Monday, was looking at a piece of code in the first project that had the pandas location or label locator, and great, I kind of understand it as when you're trying to find the label, the name of the index label. I find it easy to do that, but and then like the iLock is like when you're trying to use the index, the index number, and not the name of the index. Okay, right. So index being like the name for the observation would be using for the look for each row, right? Now, I wanted to explore that really, but I felt like I was a little rushed to get things done in that day, and I don't need to get it done in a day. I need to get it right, right? At this phase, for sure, I just need to get it right so that I can show potential employers that look, I know how to do this. It may take me a little bit of time at first, but I'm going to get it right? I'm not going to skimp on the quality, right? To meet a deadline. But that's what I was thinking of, because I want to be able to explore. I want to keep my brain open to exploring. So I want to have a flexible schedule. It's not, So I think a cautionary word of caution for anybody kind of jumping into here and watching the video, expecting that it's going to be one focus, where that focus is what's described in the thumbnail and what's described in the title and description. It could change, right? It could change. So because of the way my brain works, right? So I apologize if you're expecting that to be the case, but if you're expecting a focus, that will come. I have to go back in post, and when I go and edit the video, when I trim down the breaks, trim out, cut out the breaks and everything, I go in and edit the description and the title and the thumbnail. That's fairly simple. I can do that. Sometimes I even do that after dinner or during dinner on my phone. Just edit the description and title. Yeah. And already, I'm thinking that, I'm focusing way too much on the live streaming aspect of this than I am on the analysis part, which is the more important thing, right? That's the core of what I'm doing, and I need to make sure that I'm keeping that goal in mind. So, with that said, let's get back to looking at what I did the first 2 days. So what we did the first 2 days, what I did, looked at long tail distributions and Stooge's t-distribution briefly with the book Practical Stats for Data Scientists, and then I revisited the normal distribution by reviewing that note, fleshed out the data analyst note with the skills, fundamental skills, meta skills from The Well-Grounded Data Analyst, the book by David Asboth, and technologies, and also the toolkit, part of the toolkit, right? So some of these things, so I can kind of I can click some of those, I can check some of those off. I know database query. So Microsoft Excel, I kind of I haven't used it in so long, but the same tools are going to apply. If I know pivot tables in Python, I can apply them to Microsoft Excel. Conditional formats. I know some functions, and making very complicated functions and stuff. And also know that you can now use some other programming languages to interact with that as well, to interact with spreadsheets. VBA is one from a long time, past couple decades probably, and so I know that exists, but I don't really know much about it, aside from knowing that you can script some things in there. And now you can interact with Python. You can interact with your spreadsheets using Python in Excel, at least on the Microsoft or the Office 360 or something like that, with where they spin up a virtual machine for you, a VM or a virtual environment for Python for that instance of your spreadsheet. Right, and then so we read through chapter 1 and 2 of the well-grounded data analyst. Actually, most of chapter 2, but finished up on Tuesday. Results, and we learned about the results-driven approach to data analysis, which reminds me, I'm going to take a quick step away and try to find the book How to Solve It, because I want to look at the outline that George Polya puts in there and then try to like synthesize the two. So I'll be right back. It's actually by G. Polya. I don't know what the first name is there. The foreword by John Horton Conway. That's nice. So, yeah, I took a lot of notes in here. Right, just briefly looking at this. It's got a breakdown of the steps. So the first part is understanding the problem, right? That looks familiar. Let's look at that. Understanding the problem. Understand the problem is the first step. Always in any problem, you have to do that. Whereas in the well-grounded data analyst, we have start at the end and identify additional resources. Well, that's devising a plan, right? Devising a plan in how to solve it kind of correlates to starting at the end and then like identifying what additional resources you might need to solve it, right? And then the next thing is obtain data needed to get the, let's go back to here. Obtain data needed to get the minimum viable answer, and then do the work to get the MVA, right? So we could kind of skip the obtain the data. This could all be kind of wrapped up in the devising of a plan. Is 2 through 4. Start at the end, identify additional resources, and obtain the data. That could be part of devising a plan, that you need all of those things in order to solve the problem. And then we do the work to get the minimum viable answer. I think was the MVA, yeah. Minimum viable answer. That's carrying out the plan in Polya here. That's carrying out the plan, right? And then there's looking back, and that's iterating if necessary, right? That's iterating if necessary. Present the MVA to the stakeholder and iterate if necessary. So there's similar approaches, right? Problem solving, there's many different ways that you can label it, the process, and do that. There's also another book that I read a while ago, back in like 2020. Think Like a Data Scientist by Gotzi. Let me get that up. Brian Gotzi. It's this one from Manning. Pretty good book. It also has an approach to solving data science problems, right? The data science process step by step. In like all of these, so like I guess my point here is that like, while it's good to have the foundation, have the scaffolding and the structure, it's you don't need to stick to somebody else's idea of like what the process is. You can think about your own process in solving problems and then put a name to each of those steps, right? And dive deep into understanding what you're doing in each of those steps. So, yeah. So, preparing and gathering data and knowledge, building a product. So where is I'm trying to see where that step is, where the process is. It's probably somewhere in the beginning. Data science process. I had this like printed out. So prepare, build, finish, and then you like come back around and wrap up, revise, and wrap up and deliver. So this like kind of, this diagram kind of indicates that there's an endpoint, right? There's a way to say that we're done. We're done here, right? Whereas David Asboth's approach here is that you're going to iterate. You're going to get an answer, and then you're going to refine that answer. So I think, if I remember correctly, Gotzi did talk a little bit about with your revising and like going back and then and making this more of a circular thing. But yes, okay. You can read in live book, I think. You can highlight and annotate. You could do discussion there. That's pretty cool. Yeah, these live books are really actually pretty good here. So that's the thing. That's the thing I wanted to talk about at the beginning here. I'm not going to do it right now, but I am going to add some notes that I took from here into my Obsidian. Because I think it's good to take. It's good for your brain, I think, to take all your sources of deep storage that you have kept in your brain and bring them together, like create those neural connections between those things. And because it's so easy, like when I was going through undergraduate with college, is like I'd have calculus and linear algebra, and I'd be able to like know a lot about calculus. I'd know a lot about the linear algebra, and then like have difficulty meshing those two to some extent. But then until later in my once I got to junior or senior year, started to make more sense, the connections between them. However, like with physics, funny enough, like physics, you'd use calculus in there, and my brain was just like so compartmentalized that like I couldn't make the connection between the physics and the calculus. It was just so hard for me to draw that, to synthesize those two. Yeah. Okay. So what I want to do is get started with that after going over yesterday's stuff that I talked about. All right, so I did look at like wide and long data, and that was pretty good. I liked thinking about how to define what it is to be wide data versus long data. It's kind of weird to put into words because it seems like any definition that you create, it just seems wrong. Like, yeah, I don't know. And then what I did was starting on the data modeling project. So we did, well, we looked at the binomial variable and binomial distribution and data modeling. And then there was the chi-squared distribution as well explored. And thanks to Naviet for putting the link to, or not the link, just mentioning the all of statistics. I guess it was Larry Wasserman, or Wasserman. And somebody, Telmo Correa, has a GitHub repository of their notes for this, and used Jupyter Notebooks with Python to explore the code ideas there for All of Statistics, a book by Larry Wasserman, which is apparently highly recommended for graduate students in statistics. It's a little bit higher than my, like, not like the level that I want to be. It's more, that's more like, it's not just theoretical, but it is like more, it is applied. And, statistics is just like applied math, but thinking like statistics applied to real world data rather than these contrived data sets and just like the theoretical mathematics of large data sets and stuff like that. I don't know what I'm trying to say there. But like it just seems a little much for me right now. I think that in the future, that is a resource that I might want to come back to. I'd love to come back to that and go through that. But there's so many things to look at, so it really depends on where this journey takes me, right? If I ever come back to that. But I do appreciate the suggestion. It's always good to have some more resources, to be aware of more resources. Okay, so I took a look at the stats one there. Then I got distracted trying to download title music for title. Let's see, and so we fleshed out the data modeling note, giving a name for this. So this definition of data modeling kind of differs from what I understand data modeling to be in the data engineering sense. Repetitive data cleaning tasks, that's a data engineering thing, but like that's not really what we think of when you were thinking of data modeling. We think about like tables, SQL tables, and or relational database tables, and the entity relationship between entities, between tables, that type of thing. So, and like think about like dimension tables and fact tables. So dimensions being the like measurements, or not the measurements, fact tables being the measurements, and then like dimensions being like the variables and descriptors and stuff. Descriptors of an entity or identifiers of an entity. And where I'm saying entity, like of an observation and stuff. So, yeah, deduplicating source data. This isn't what I think of when I think of data modeling. This is what I think about when I think about data wrangling. defining business entities, concepts, and activities, that is closer to what I'm thinking of when you're thinking about data modeling, is deciding which entities and concepts you want to capture. Deduplicating source data, that is kind of I think of with data engineering. That's actually like where we'd be thinking about more about data refinement and data, what do you call it? Validation and cleaning. Restructuring raw data to a format more useful. That's wrangling. That's wrangling. Zooming in or out, altering the level of granularity. Yeah, I think I don't know. I think it's good for me to be aware that like maybe analysts speak about data modeling differently than data engineers. So that's something that was new to me. So I'm glad to learn about that. So today we're going to do linear regression in Python and learn how to do that. So I'm going to create a note for that. When I come back, we'll create a note for this. Actually, we could just do it now and do this article on to read, and then I'll just put it to there. And then what we'll do is move this to tutorials. Okay. Yeah, it takes. Okay, so it's there. Right, and so I'm going to take a quick break. Been going for 45 minutes. Not quite enough to trigger the break there, but that should be okay. I'll be back pretty soon. I'm gonna take like a 15-minute break, I think. So I'll be back in a little bit. Okay. All right, let's get started with this here. Okay, so this is very weird. Yeah, I gotta edit something here. All right, that's weird. All right, so what I need to do first is to get a folder open here with do we call this real Python linear? Yeah, let's call it real Python. Linear regression. Yep. And here, and I'm going to create a notebook. Let's call it Linreg. IPy notebook. Where did it go? Because it didn't save, I guess. There it goes. Get that there. Linear regression in Python. I'm gonna actually, let's copy this image. Down. regression in Python. So, that down. Let's get a list of the things that we're going to do here. Regression. We're going to have linear regression. And we're going to add Python packages for linear regression. Simple linear regression with scikit-learn. And multiple linear regression. Polynomial Regression. And advanced linear stats models. Oh, and beyond right here. It is beyond linear. All right. Let's get that one. Okay. Ooh. Up a little bit as well. So I have an interactive quiz I'd like to do in the future, but not today. I'd just like to come back to it a couple days later to use a little bit of recall, solidify those neural connections a little bit further. Actually, I'm going to keep this one, I think, and then I'll... Yeah, because that's at the end. And then where it's up above. Get the code. Which is okay because we'll have it alongside the other stuff here. Let's see. Linear regression. Let's get some notes up on what regression is. You know what I'll do? Resources. There we go. That to yeah, and so what I'll do from here, let's search for notes. Really? Okay, so that's the only one where we contain the word. So we also want to search for the phrase, and then we have to search for the exact match, I think. We search for is this going to get linear and regression? Yeah. Boopity-boo. Alright, so I'm going to flesh out some of these notes as well. Readwise articles. Usually what happens here is that there's duplicated information here. And there it is. Okay, so this was a readwise thing. Feedback is not there. Get rid of that. Just use that. Highlights there. Okay, definition is there as well, so we can copy that. So what I'm gonna do is move this right out here and do this. Let's see. Let's oops, sorry. Yeeting that. Yeet, yeet, Mickey. Okay. Yosh. Okay. Using that down, visualizing data with Seaborn. So we did this earlier in the week, I think. Last month. Earlier in the year. Yes, we did that. And interesting. Using ggplot Python. Did that last year. Yeah, we did this earlier this year. So it's not surprising that these are showing up in the places where I've already done. That linear regression shows up in the notes that I've already taken for this year, because it's such a fundamental idea with forecasting for data analysts to use, right? So it's such a useful forecasting tool. And so we also have Seaborn flashcards here. Data analytics, and I think that was the Wikipedia as well. Right? Yeah. And then there's 15 questions to test your statistics knowledge. Is interesting thing there. What I need to do, I think, with this is to create some flashcards from here. Yeah, I don't remember how. Oh, because we did the... Yeah, I think it was with the highlight. Yeah, I need to work through these as well. Work through that note to make it easier to work with there. We also have doing data science. And that's a book note, I believe. Oh no, from my data science notebook. Oh, that's weird. Okay. Oh, wait a minute. The ML classification, linear regression for recommender system. That's what it was. What was the doing data science note that I had? Book notes? Oh, you know what? Oh. Those are my notes. I gotta take care. I gotta like go through that again. Right. We do have that one. So what I'll do is I'll add an annotator. Annotation target is I don't know if this actually works. Yeah, it does. Okay. Yeah, we have a book. There we go. Nifty. Nifty McGift, eh? Oh, that's not what we want. Really? You can't, like... There we go. I need to hotkey this in some way. I don't know what I'm going to use, though. Alt-Shift-A? I don't know what Alt-Shift-A does. Maybe I'll use that. File, my notes. There's that. I can can actually add in Alt-E to add book note. Yeah, there we go. Related notes. Yeah, I could put it with my notes. So local cover image. It's fine. Actually know what the ISBN is. Oh, we already got the publisher there. Publish date and publish total pages. Yeah, with the path for I don't know where any of that stuff is. The description is book. Or where that's going to be. Setting this book. Okay. Yeah, I'm not really sure. If I'm going to flesh out all that other stuff, it's not really that important. I do have that book. I wonder if there's been an update. That's also in R, so it's like not really. It is. I never really went through the examples there. Okay, so now I have my linear regression notes here. And I can also use linear regression in Python as well. It's another related note. Yeah. So, yeah, that's the mathematics behind it. So this is also mathematics. Statistics as well. Okay. Yeah. No, it's not shifting over. Okay. Yeah, so that should work now. There we go. So it wasn't working before. You're just staying in the center. Yeah. All right. Okay, so I close that down. I'll get started with this one here. Okay, so linear regression is a foundational statistical tool for modeling the relationship between a dependent variable, one or more independent variables. It's widely used in data science and machine learning to predict outcomes and understand relationships between variables. I should take some some mathy stuff there. So, terms. I'm going to use terms here. Yeah, so I'm just going to take their definition here. A linear equation. Go. Okay, so it can be straightforward with the help of third-party libraries such as scikit-learn and stats models. I think we have both of those. We can probably just import them right at the top here. Well, we'll just work through it as we go. And implementing linear regression in Python involves using libraries like scikit-learn and stats models, fit models, and make predictions. The formula for linear regression is that. Actually, I have it here. Y bar. So they just use these as alpha being a alpha actually being the B, the beta not there, with beta being a vector of coefficients, and X being a vector of the observations. Right. And the alpha, no, the alpha they're doing here, well, all right, well, linear regression, we're just doing it with one X value. You can expand that to vectors of over multiple variables. They're using epsilon as the alpha there. I think. Maybe I have that wrong. We'll get to it, I guess. I don't know what they're using epsilon for. Like the band around, like the plus or minus the epsilon for the confidence level or something like that. Simple linear regression involves one independent variable, whereas multiple linear regression involves two or more. The scikit-learn library provides a convenient and efficient interface for performing linear regression in Python. So we're going to implement linear regression in Python. Typically follow a 5-step process: importing necessary packages, provide and transform data, create and fit a regression model, and evaluate the results and make predictions. So let me try to flesh this out. So take some notes onto here. Terms, and let's say like process maybe. Like, I guess import, I'll provide like get, extract. Let's use those ETL terms there. And fit a regression model. Evaluate results and test your or you could test the you could validate it, see how strong of a fit it is with some metrics for measuring the error. Making predictions and use it to make predictions. Okay. This approach allows you to perform both simple and linear, or multiple linear, as well as polynomial regression, using Python's robust ecosystem of scientific libraries. Regression analysis, one of the most important fields in statistics and machine learning. There are many regression methods available. Linear regression is one. Okay, so we're gonna go into, let's see, what is regression? So it searches for relationships among variables. For example, you can observe several employees of some company and try to understand how the salaries depend on their features, such as experience, education level, role, city of employment, and so on. So it's a regression problem where data related to each employee represents one observation. The presumption is that the experience, education, role, and city are the independent features, while the salary depends on them. Okay, so similarly, you can try to establish, so the target variable here is going to be, what are we trying to do? Probably like salary. Try to understand their salary. So our target's probably going to be salary, and then the dependent variable is probably going to be salary, and then the independent variables, we're going to look across the features, experience, education level, role, city of employment, so on. Okay, so the presumption is that, yeah, right, they're independent features. Similarly, you can try to establish the mathematical dependence of housing areas, housing prices on area, number of bedrooms, distance to the city center, and so on. Generally, in regression analysis, you consider some phenomenon of interest with and have a number of observations. Each observation has two or more features. Following the assumption that at least one of the features depends on the others, you try to establish a relation among them. And in other words, you need to find a function that maps some features or variables to others sufficiently well. Dependent features are called the dependent variables. Outputs are responses. I think I have notes on that, don't I? Lurking variable, environment variable. So this is weird. Okay. Let me do a search, I guess. No. That's me. That's why I'm a little foggy. I think my focus factor. Yeah, I guess we don't have. Weird. I thought I fleshed out a note for that. Maybe it's too basic. What it was. It's been a small one. Okay, let's go in here. Maybe independent variables. Something different there. Nope, still in there. Oh yeah, okay. You gotta go. There's gonna be so many things with outcome. Response variable. Output. Yeah, it's weird. Regression problems usually have one continuous and unbounded dependent variable. The inputs, however, can be continuous, discrete, or even categorical data such as gender, nationality, or brand. Actually, there's one other term I wanted to search for. Oh, here we go. That's where it was. That's what I was looking for. Commonly referred to as a feature. could also be independent variables, inputs, regressors, or predictors. Yeah. This doesn't necessarily need to be in rectangular data. Get it in a data frame. But I guess it's okay there. This was my middle school thing. Right, writing stories about that. Yeah. Feels a lot more manageable now. Okay. Regression problems usually have one continuous and unbounded dependent variable. Common practice to denote the outputs with y and the inputs with x. If there are two or more independent variables, then they can be represented as the vector x, where r is the number of inputs. When do we need a regression? So you need regression to answer whether and how some phenomenon influences the other, or how several variables are related. Okay. Oh, wait, did it? Oh, yeah, it did. Never mind. There we go. It just adds it to the end there. Nifty. That's a pretty neat feature of Obsidian. Fleshing out my note on linear regression here. Huh. Regression is also useful when you want to forecast a response using a new set of predictors. Has to do with the appearance, so. So it's a JavaScript thing. Yeah, that's kind of what I want to have happen. That's what I want to have happen now. Wait, is that push not going? There it goes, okay. It might not be updated there. OmniSearch, but I'm not using OmniSearch. I don't know why. I started to use it, but then I think it was just too slow, or like something ended up. I think it was on load. It took a long time to load or something. Why would you do it that way, though? This is something I keep an eye on. This is already implemented. I think, oh, wait a minute, maybe it isn't. Wait a minute, yeah. I think it's, yeah, because when you hover over, it just gives you that, but then you can just hover over that. I mean, it's just, I don't really, yeah, I don't think it's useful. That shorter footnote is interesting. I just wonder when it's going to become available. What does it need to, what needs to happen in order to get that in there? Better footnote, enable shorter footnote, disable better, enable better footnote, yeah. Maybe that's why it's not submitted there, because it does conflict with the better footnote. Even though I don't... Yeah. I don't like that. The tidy footnotes seems interesting. I wonder what this one is. Shortcut. Insert a new named footnote marker, citation. Excuse me. Just about time for lunch, too. I'm gonna probably get going with that soon. Yeah, I think I'm just gonna take a quick break, and then I'll come back and finish up this like first part and get to the first coding block. So regression is used in many different fields, including economics, computer science, and social sciences. Its importance rises every day with the availability of large amounts of data and increased awareness of the practical value of data. Yeah, so I'm going to come back and do this here. Start there. Yeah, the problem formulation, regression, performance, and a simple linear regression. Right, this example there. Yeah, so we don't even get to code until a long time. Python packages for the regression. Right, I'm pretty sure I have NumPy, scikit-learn, and stats models. Underscores highlighted there. Um. Okay. Yeah. I think I'm going to flesh out notes. That's what I'm going to do, is to flesh out this note for multiple regressions and stuff. Yeah. Yeah. Use cases, process, pipeline. I need to come up with like some... it's fine. I don't know. I was thinking of coming up with a structure for the hierarchy of headings. Have them adhere to a certain format. That's okay. All right. Yeah, I'm just like, ooh. I need to get some rest. Like, just been having not good sleep for the past couple weeks. So definitely hurts the brain. Yeah, I'll be back in. Quick break here. Let's see how that works. Just want to test one other thing here. Doing some testing here. Hang on. But that works. Not bad, but whatever. And this is too convoluted. Okay. Okay. Hopefully, I'll remember to add stream markers and stuff. That's what I gotta get in the habit of doing. So that when I go back and edit, I can, yeah, give a name to it or something. I think it's like better to just like give a name as you go, but like I don't know. There's like a plugin that you can use for that. Yeah, but I think it's with StreamerBot, which you have to pay for. And I don't want to do that because I'm broke. So, yeah, it'd be nice to use though. I'm gonna I'm gonna take a little sojourn LinkedIn for a second and do the puzzle games for today. Yeah, don't use AI. Are you using an AI tool to qualify candidates? Bit of a edge case, catch-22. I mean, yeah. Who's viewed my profile? Nobody? Nobody that I know. Past couple days. Okay, where's the I wish they put the puzzle things down here. Instead, I think it's just like puzzles or something, or games. Yeah. Okay, so give me right off the bat there. Lots of gimmies. That's right. Okay, so there's at least one of each here, which means that there's two of each. We don't know what that last one should be. Okay. Oh, we gotta fill it. There we go. This should play out easily now. There we go. Solve Queen's puzzle. What are we missing? Oh, purple. I was like, what? Goes for Delta Airlines, and life is a fucking nightmare. Oh, these are just Greek letters. Psi, epsilon, epsilon, epsilon. Opposite of heaven is hail. Fell off a wall. Well done. That ought to hype you. Yell? Gripped? Held. What? Alright. Whale. Whale. From head to tail. There we go. Alrighty, that's fun. Alright, let's go back here. That's weird. Why is that going on there? Something's weird going on. There we go. Another thing that's weird here. Let me check on something. Overlay. It's so weird. If not cursor in this region, but that's the region where I'm in. Oh, that's backwards, isn't it? Yeah, that was backwards. So weird. That's weird, honestly. I don't understand. Yeah, I guess it's fine. Okay. Just so weird, like, logic going on with my advanced scene switcher. I just didn't really think it through. Oh, boy. Okay. Oh, gosh. Okay. All right, so let's try to get through some of this with the problem formulation. So linear regression is one of the most important and widely used regression techniques. don't know why we're still focused on there. Yeah, okay, there we go. So when implementing linear regression of some dependent variable y on the set of independent variables of the x vector there, r is the number of predictors. You assume a linear relationship between y and x. Yeah. So a single output given by a set of predictors. So that's the regression equation, and we have it up there. I'm just going to leave it as math, actually. Find estimators that such that there it is. So we have alpha, so let's say variables in the description. You could use is that what it is? No. Did he indicate bold? I thought it was vect, but yeah. If this works. I don't think it works in Gedeck though. You know, it does. Interesting. I don't think this works because this usually has to be in the preamble, right? Yeah, that's not going to work. If you use package physics, doesn't work. That only works in the preamble. You can, however, like set commands. That's pretty interesting. Okay. I think it's in Gedeck. If we could do it's still italics. Oh, that still works. That's so weird. Oh. Okay. Call it the vector of independent variables. Oh boy, okay. Ugh. Just capital. Pretty sure this is a bar epsilon too. Yeah, it is. Okay, cool. I guess they're saying estimators. In this formulation, we have alpha not or alpha hat and beta hat as the estimators. Yeah, there they go. It's just right there. And so what we'll probably do is to call it this. I'm gonna go on lunch pretty soon. Let me try to work through this first part here. Predicted weights. Right, the function should capture the dependencies between the inputs and outputs sufficiently well. Hmm. I don't know where that came from, honestly. Needed a predicted response. Observation, yeah. That's why we're going up to n. N is our sample size, or our data set size. Hmm. All right. That's a method of ordinary least squares. Okay, I'm gonna take a break. We're gonna take a look at the Regression Performance, which there's no notes on that, but we're gonna get the simple linear regression to do the problem statements and stuff like that. Yeah, I just really want to make sure that I fully understand. It's been a while since I've engaged with this stuff. It's a pretty important topic. So, taking lunch. Be back in about an hour. We should get the countdown timer going. All right, let's get back. Where to leave off with regression performance. So let's get that going here. Let's see. All right. Variation of actual responses occurs partly due to the dependence of the predictors. However, there's also an additional inherent variance of the output. Right, and we wanted to get the coefficient of determination. Coefficient of variation. Got that one. Let's move this to general notes, because we're going to do that as well. And r squared. We have that. Okay. Yeah, okay. Let's back up onto here. Coefficient of determination. Right, so denoted as r squared is the let me see if I can remember this. It's the amount of variation in the amount of variation in the dependent variable, which can be explained by the model, basically, right? By the line of best fit, right? Or the dependence on X, specifically on the of the inputs. Okay. Amount of using the regression model. I don't know why, like, is this? Does that work? No, bold symbol doesn't work. I wonder if I can do it as... Looks the same. I don't know why the bold doesn't work. Okay. Let's see. I put this up here. So I haven't been taking good notes here. Like what I've been doing here, what I've used. Notes created today. We did. Oh, notes worked with today, linear regression. Yeah. Oof. Okay. By an independent variable, or the list of independent variables, right? Set of independent variables. Oh my god. Woo! Some determination. Sum of squares of residuals. If the sum of squares of residuals, yeah, are just like really awful. The total sum of squares. Yeah. If your predictor's really bad, you could have a negative r squared. That's not good. Ooh. Larger r squared indicates a better fit. Well, yeah, I mean up till 1. It maxes at 1, but it can be negative as well, right? Because of this, yeah, we should put that in there. We should put that calculation. It's the some squares of the residual, right? And then the total sum of squares, which I believe is something like you're gonna go the I to n and then do sum of the squares. Yeah, if you're minimizing the residuals, then it's 0. The residuals are 0, but then the residuals could be really bad. TSS. Okay, Oh boy. The total sum of squares, I thought was, is it just each observation? I think. So when it's exactly 0, that would mean that ratio is 1. Oh, but that just corresponds to a straight line at 0. Yeah. Right? Yeah, it has to. Okay. Or it's the line y is equal to 0 is the predictor that makes it r squared equal to 0. Or I think it's actually the mean. Is it the mean? No, I don't know. Can't be. Guess we'll learn more about that. Simple linear regression. Very linear regression. Simple case of linear regression. There's a single independent variable, right? The vector is just... I don't like this formulation here. It's just the vector with just one element. Following figure illustrates the simple linear regression actual response, right? So I should just copy this image. I'm going to put that right to here. Implementing simple linear regression, you typically start with a given set of input-output XY pairs. These pairs are your observations, shown as green circles in the figure. Right. The leftmost observation has the input x is equal to 5. The actual output is 5. The response 5, and then the next one's 15. Actual responses, yeah, I agree. So we have to calculate the optimal values of the predicted weights that minimize SSR and determine the estimated regression function. Right. The value of B0 is also called the intercept. Of course, shows the point where the estimated regression line crosses the y-axis. It's the value of the estimated response. So let's, I don't know if I want to put that over there. So we have terms here as well. I do want to flesh out the sum squared residuals, which is going to be the SSR. And then oh my gosh, what the heck just happened? No, I don't want that. What is... No, what happened? Did not want that. I do not want this. Little song. Value of estimated response. So we also could do the intercept, right? The intercept is value B naught. How to minimize the distances that are up. Okay. Oh gosh. Okay. Multiple linear regression. It's just. Yeah. Mm-hmm. Yeah, and then with 2 dimensions, it resembles a plane, and then beyond that, it's blah 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 blah. 3-dimensional spaces and crazy stuff. Yeah. I'm trying to think of what it is in 3 dimensions. Is it like a... Is it the intersection of all combinations of planes? I'm not sure. So that would be like 3 planes intersecting, or and then be like the convex hull of that or something. I don't know. I don't know. So at least a thought that comes up that I never answer. I mean, so, polynomial regression, we talk about that with linear algebra. So I'm probably not going to touch much of in this go around here, in this 90-day block here. Yeah. What is it? Yeah, so linear algebra, kind of like one of the results that we like find with abstracting vector spaces is that things are linear when you don't think that they really are. Like, yeah, you can think of a polynomial as a linear problem in the right context here, even though if you're thinking on the you're thinking of the polynomial graphed on a Cartesian plane, then you obviously wouldn't say that that's linear. I think because it's not. Yeah. Yeah. It wouldn't necessarily be linear. But there's a mapping, right? There's a mapping from the polynomials to a linear space, to a linear vector space that you can do, and then you just solve it from there. And it is linear, actually. Let's see what they say about this, though. You can regard polynomial regression as a generalized case of linear regression. You assume the polynomial dependence between the output and inputs, and consequently, the polynomial estimated regression function. So you have to like take a guess at what the polynomial is, or the order that the polynomial is up front, right? And you could just do some guesswork, I guess, right? That's just do some guesswork and see like which one fits the best. But of course, when you start using too many higher order terms, you run the risk of overfitting. It's going to be fitting too closely to the data, so that if you get a new data point, even in interpolating, even trying to interpolate from there, it might not fit well. Might get huge errors from that. So you assume the polynomial dependence, right? Polynomial estimated regression function. In other words, in addition to linear terms like b1 bx, or b1 x1, your regression function f can include nonlinear terms such as b2 x1 squared, b3 x1 cubed, or even some interdependence between the two variables. Yeah. Oh, that was another thing. Yeah. Yep. Could do it that way. Simplest example of polynomial regression has a single independent variable, and the estimated regression function is a polynomial of degree 2. You remember that you calculate the coefficients there to minimize, or like the estimated weights to minimize SSR, and these are the unknowns. You keep that in mind, compare the previous regression function with the function blibbity bloops used for linear regression. They look very similar and are both linear functions of the unknowns of your estimators there. You're trying to estimate those. This is why you can solve the polynomial regression problem as a linear problem with the term x squared regarded as an input variable. In the case of two variables in the polynomial of degree 2, the regression function has this form. I want to say like that was like before I even got into linear algebra and like finding out, like working out some problems that like, right, you could do this, like that was fun. Like I remember doing similar things like that, where I was like, oh wait, but I'm trying to find these coefficients, so I'm just like, I can solve that. You just invert the problem a bit, right? We know what the input values are. Let's try to solve it. The procedure for solving the problem is identical to the previous case. We apply linear regression for 5 inputs, x1, x2, x1 squared, x1 times x2. Right. And the result of regression, you get the values of 6 weights that minimize the SSR. So yeah, you need 6 weights for doing a squared, for doing a polynomial. So of course, that's why like it gets overfit pretty fast, is because the number of coefficients that you're trying to solve for just gets so much exponentially larger as you increase the power, the order of the polynomial linearly. Yeah. Underfitting and overfitting. One very important question that might arise when you're implementing polynomial regression is related to the choice of the optimal degree of the polynomial regression function. Yeah. The degree. That's what I was trying to think of. The order, the degree, whatnot. There's no straightforward rule for doing this. It depends on the case. You should, however, be aware of two problems that might follow the choice of degree: underfitting and overfitting, right? Underfitting occurs when a model can't accurately capture the dependencies of the data. So let's get that. The problem with overfitting is that it doesn't generalize. Underfitting doesn't even capture its own data, but then like overfitting doesn't generalize. So underfitting occurs with a low R squared with known data and bad generalization capabilities when applied with new data. Right. So the thing with underfitting is that yields low R squared with known data and bad generalization. So for both, it's bad for both, right? Overfitting is good for the data you have, but pretty bad at the generalizing, right? So there's a balance in between the two, right? You want to just find the right fit, the optimal fit. Model learns the existing data too well. I wouldn't say too simple to complex because you can overfit like with a really low degree polynomial. Yeah, like if you have just I don't know. I guess I don't know. I don't know if I want to say too complex. It's I would say it's too close to the existing data or to the training data. Complex models have many features or terms and are often so yeah, it's too complex. Generalize well. New data or validation data is probably going to be low R squared as well. And so I'm just going to take this and copy it. So what we're going to have with this, the training data is going to be a high R squared. So close to 1. New data will have a low R squared. Right. Right. Okay. So like here's probably a pretty good example that this R squared for the linear one is pretty bad, right? It seems like it's underfit. This one seems like a good fit here. But this could be overfitting, right? Especially in extrapolating outside of the min and max values for your X and Y, right? So if you think of like a box, that's like kind of like the range of your model there. And then this is just completely overfit. This is fitting exactly to the data with a degree 5 polynomial. So they usually go with odd number order or degree for some reason. I forget why. So top left shows a linear regression line that has a low R squared. Might also be important that a straight line can't take into account the fact that the actual response increases as X moves away from 25 and towards 0. This is likely an example of overfitting. And then you have like, oh my gosh, there were like people just trying to do like very, very, very crude modeling of COVID data. Assuming that things weren't like that assuming a static data set basically, and trying to like extrapolate out from the existing data, in doing it with a time series, which, you know, it has its problems when you try to fit linear models to time series. Like, and the main problem is that you're assuming that all of the parameters are static, right? And that there's things not changing. And that absolutely was not the case with COVID. You know, every day, every week, every month, there was different actions taken to try to limit the growth of it, try to yeah, you know, and like some worked, some didn't. Some, you know, and then like you have, it was so complex. Like some worked, some you know, some were beneficial, some had no effect, and then some were like unintentional, you know, like had side effects of like people getting too confident in being around other people. Oh, we're gonna have air filters and stuff like that. Like, oh yeah, the air filters will save you. And so they felt safer going into those environments, which was not good. Just came with false sense of security and stuff. So yeah, there's always a risk. Like the assumption when you're doing these models is that your underlying parameters are not changing, right? The underlying data or the population that you're sampling is not changing. The top left plot shows a linear regression line that has a low r squared. Might also be important to that a straight line can't take into account the fact that the actual response increases as x moves away from 25 and towards 0. This is likely an example of underfitting, right? Okay. I'm not going to go through all. I pretty much explained a lot of them. Ooh, Khan Academy we're referencing. Let's see. Let's yeah. Which line fits the data graph? Well, it looks like A does. I can hope. Okay. Now let's actually get into the coding. All right, finally. Okay. Time to start implementing linear regression in Python. To do this, we'll apply the proper packages and the functions and classes. NumPy is a fundamental Python scientific package that allows many high-performance operations on single-dimensional and multi-dimensional arrays. It also offers many mathematical routines. Of course, it's open source, which is always good. You can actually work on NumPy. You can work on NumPy. Even have a NumPy tutorial. Your first steps into that, and this was from 2021. Interesting. I don't know how much is going to be used anymore. It still underpins a lot of pandas with like some of the broadcasting, but the data types are the problem with NumPy and other packages that that depend on it, like SciPy and scikit-learn. That like a lot of the issues with like scikit-learn is that like you have to, everything has to be in a numerical, in some kind of numerical matrix or something similar like that. There are like they have tried to abstract away some of that with taking in pandas and pandas data frames and the pandas series as inputs to some of the arguments into some of the functions, but yeah, so we've, oh well, that's a pretty good model there. Stats models, look at that over there. Actually, I want to move these over here. That over there. Virtual environments. Yeah, I know about those. We got them. Scikit-learn's also open source. Got linear models over here. Non-negatively squares, ordinarily squares complexity. Okay. Lasso regression, yeah, you're like adding penalty terms. Prefers solutions with fewer non-zero coefficients. Okay. All right, so let us flesh out this process here. We'll do the process for simple linear regression. Oh wait, we have an up for that. Okay. There we go. 5 basic steps. So, right, just like we talked about in the linear regression here. Process in Python is usually to import necessary packages. Classes need. Then extract and transform data. So it's going to be to provide data to work with. The appropriate transformations. Create a regression model. Get it with existing data. Oops. Of model fitting. There's satisfactory, and then apply the model for predictions. That's usually the process there. Ooh, gosh, I should roll on the foam roller. Roll out this back here. Okay. So we're gonna do this process here. So we're gonna do import packages and classes. And linear modeling import OLS, or it's just linear. Pretty sure it's just linear regression, right? Yeah, it is. Okay. Now you have all the functionalities that you need to implement linear regression. Fundamental data type of NumPy is the array type called NumPy ND array. The rest of this tutorial uses the term array to refer to instances of the type NumPy.nd array. You'll use the class scikit-learn linear model.linear regression to perform linear and polynomial regression and make predictions accordingly. So step 2 is going to be to provide data. Yeah, we got our kernel going. Why it takes so long to load those files, those packages for some reason. The import, we do imports. Yeah. Supposedly the UV virtual environments are faster. I haven't checked that out though. So we're going to create some data here. Five, 15, 25, 35, 45, 55. Why didn't we just do a range? MPA range. Reshape. Y is going to be the array from 2, 38. That guy there. So we got data. Okay. So he's got two buddy boops, so we can do the shape. Of course, those are the shapes. 6 rows, 1 column for X, and then 6 rows for Y. Spet 3. Create a model and fit it. Create a model and fit it. Fit that model. I really wish that I did this differently. Like, what happens when I click on this? I think what we want to do is to like focus. I want to do something. Focus on like one screen or something, right? Yeah, I gotta figure out how I'm gonna do that. Gotta think that through a little bit better. It was good before I did anything else. Create a model is very simple. Just, well, you start a model object actually, and then you start to fit it from there. You feed it data to fit to, and represent the regression model. Instance of linear regression, you can provide several optional parameters to linear regression. Fit intercept is a boolean that, if true, decides to calculate the intercept to be not, or if false, considers it equal to 0. Defaults to true, and then normalize. Right, okay. Are we playing with any of these? Copy the true by default. Why? What would happen? Overwrite the input variables. What does that do? Yeah, I don't know what that does actually. N jobs is either an integer or none, so it represents the number of jobs used in parallel computation and defaults to none. Usually means one job. -1 means to use all available processors. So we're going to fit our model to our X and Y data. We get a linear regression model. And so if we see this, we see it's fitted. And you can go right to the documentation for linear regression now. So this is in... I don't know. Let's take a look at actually, I don't think we need to do that. We can just look at the requirements. Scikit-learn 1.6.1 is the version that we're using for this. Okay. So with fit, you calculate the optimal values and the weights using existing input. It's the model to itself, which is valuable. So that's why you can replace the last two statements with this one. The statement does the same thing as the previous two, it's just shorter. Get results. Once you have your model fitted, you can get the results to check whether the model works satisfactorily, and to interpret it. Obtain the coefficient of determination R squared with the score called on model, right? Okay. R squared. The scoring our training data on that, and then we can do a print coefficient of determination. When you're applying score, the arguments are also the predictor x and response y, and the return value is R squared. Yeah, that trailing underscore I think means that it's a model parameter that's estimated. So it means that like it may not be available, right, at first, unless you've run the model, unless you've run the fit, right? Unless you've estimated it. I think, right? We can do that. We can test it. I can test that hypothesis. So if I do like it should. I think it's either going to come up with an error or none or something. Yeah. So it has no attribute that because we haven't fit it. So if we fit that to our data and then we do the intercept, then we get that, right? Code above illustrates how to get B0, B1. You can notice that intercept is a scalar while coef is an array. And so by convention, trailing underscore indicates that an attribute is estimated. In this example, intercept underscore and coef underscore are estimated values. So the value of B0 is approximately 5.63. This illustrates that our model predicts the response 5.63 when x is 0. Right. At the x-intercept, the value b1, 0.5, means the predicted response rises by 0.54 when x is increased by 1. Yeah. You'll notice that you can provide y as a two-dimensional array as well. Yeah, in this case, you'll get a similar result. It might look differently, though, right? Huh. Oh, I should have just kept my code. And then, oh wait, you can reshape. Huh. Very similar to the previous one, but in this case, intercept is a one-dimensional array with the single element there, and coef is a two-dimensional array with a single element. Yeah. Is that for multiple regression? If you're... Yeah, I don't know. If you're trying to target multiple targets or something and do multiple linear regressions. I don't know why that is the case. Y predator is modeled up. Predict. We're going to look at a predicted response. For all these. What's up with the... I'm surprised that it goes in line. It doesn't do... Yeah, this is weird. So when applying predict, you pass the regressor as an argument and get the corresponding predicted response. This is a nearly identical way to predict the response, especially with the yeah. Yeah. Alrighty. You multiply each element. So if you were doing it, it's just easier to use that because of the, yeah, well, it depends on if you want to like print out the model, then you have to write some code then. Yeah. The output here differs from the previous example only in dimensions. The predicted response is now a two-dimensional array, while in the previous case I had one dimension. If you reduce the number of dimensions of x to 1, then these two approaches will yield the same result. If you reduce the number of dimensions of x to 1, then these two approaches will yield the same result. You can do this by replacing x with x reshape -1. Okay, can we try that? Because that sounds crazy and dumb at the same time. Okay, x linear. Yep, it goes up 0.54 every step there. X revel. look at multiple linear regression, so we're going to do combination. Maybe import. And provide data. So, I mean, we already have the imports, but I mean, just as a practice, I guess we're gonna do this so that we can get some memory going on. scikit-learn dot linear model regression. We're gonna do a X and Y there. Okay, X is that one, so we have two predictors there. Example, multiple linear regression. Create a model and fit it. What we want to do is to go with F4 getting me results. I'm actually just pick our previous code here. I'm not gonna bother with that. Wait, what is it when you refer to an earlier cell? When you refer to, like, how do I do that again? No, it's not that. There's actually something to do with the cell ID, right? So use the cell ID. Oh, so it's a problem with the... Okay, so it's not exactly the same thing. There was a way to do that. Sucks. There we go. Drop it down. What we could do. Yeah, so slope is interesting because then you get two slopes there, right? Yeah. Forget, like, I forget what hyperplanes do. Like, 3 or more dimensions. If you fit them all through the origin, then they won't intercept anywhere else except for in the origin. But, like, what happens? Like, that's not what I understand. Is it like the values on the line where they intersect? I don't know. I don't know. Okay. I'm gonna need a break in a minute. Let's do step 5. We're gonna get the response. So let's see if I can. So what I'm gonna do is get our previous things, right? Previously WAPRED model predict. We just do that. Is that all we do? Yeah, that's what it is. Huh. Right, and so in this case, we have a different thing going on here. We can calculate this. Wait, actually, let's just do this first. We're going to sum the is this like a dot product thing? Because the model co-op, yeah, it's got to be a dot product. Right? Because if we're doing... we do X and we do model GoF. That's got to be the dot product. That's first array times this one plus that other one, so it's got to be 0.25, that's the first output. The second one, this one, right, it's just the dot product of all these things, or the yeah, I think so. Pretty sure this is. I'm pretty sure that's what that is. Applied to new data as well. Predictors, right? Rightio. Yippers. Gonna take a break. We'll come back, do a polynomial regression with scikit-learn, and then we'll go beyond linear regression. And I think we're going to be doing a lot with advanced linear regression with stats models, but I'm not sure. Let's see. Maybe not. Maybe not. Maybe not too much. Let me actually do this. I can just reload. Yeah, there's a bit here. Actually, there's not that much. Yeah. Okay, I'll be back in a minute.
you
Polly whoop. Whoops, whoopsie. All right. Let's see. What are we doing here? Oh boy, this day after day, just rising blood pressure levels every day. This week is terrible, not good, awful, really bad. Don't like it. Okay, so Polynomial Regression with Python. Let's see. Let's go import some packages. Some packages. Step 1 is to import the packages and classes. So we're going to import. Let's see if I can find the numpy as MP, and then we want to import. Where's it? Like from scikit-learn dot Wait, did I already do this? No, I didn't do this. I thought I did this. Multiple linear regression. Oh, never mind. Okay. Not polynomial. Is it linear model? No. Poisson regressor. Ooh. That sounds fun. Pre-processing. Maybe it's with stats models? It's not with stats models. Oh, you need pre-processing. Oh, you do just do linear model, but then you do polynomial features. It's transformation you have to do. And then, does this have logistic? This does have logistic regression. I am surprised that they didn't go with... Oh, well, I guess because it is just linear regression. Logistic regression... Yeah, it's still a different thing. Okay. Oh, it's actually 2A we gotta provide data. And then we gotta transform after that. So, it's interesting because I'm pretty sure that you can just do MPA range, and then you can do... You done messed up, AA Ron. Oh, what's going on? Right, the stop, the start and stop, and the step. So I can start at 5. I can stop at 55, and I can do a step of that. And I think it's inclusive, if I remember correctly. R shape, not reshape. It is not inclusive. I think it reduced 56. It does include it. Weirdly enough, as it is, that is the shame. That is it. So we will do a y is equal to array. If it 825 32. There we go. To be or not to be, we gotta transform and input data. Right, so you have to input and output in a suitable format. Keep in mind that you need the input to be a 2-dimensional array. This is the new step that we need to implement for polynomial regression, right? So you need polynomial features, right? Degree. Wait, what's the difference between degree and order? Isn't that the same thing? basis functions. What the shriggity frig? Where is the polynomial features thing? Wait. Blah, 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 blah. There we go. Oh, order is not, okay, order of the output already. Dense case. Order is fat, F is, I don't know what that means. C or F? What that means. Spline transformer. Yeah. Alright, so we need to create a transformer that is more than meets the eye. Include bias. We don't want a bias. What is bias? Right. Include a bias column, the feature in which all polynomial powers are 0. A column of ones acts as an intercept term in a linear model. Right, the column of all ones in the beginning, I guess. So we're gonna go through 0, apparently. Is that what we're saying? I don't know. What does that mean? I don't even know what that means. So degree is an integer 2, right? So the by default represents the degree of the polynomial regression function. Interaction only is a Boolean. False by default that decides whether to include only interaction features. What are interaction features? What? Like, these are terms that we haven't talked about. Is that the like x1 times x2 or something like that? Or no, that I don't. Wait, yeah, I don't get it. Okay. Prayer. We can just fit that on x here. You have to tell the transformer to transform, otherwise it will not transform. So actually, let me see this here. Polynomial features include bias. Okay. So by convention, this is like we put the underscore there because we have transformed it. X is equal to Why would you ever... Why would you ever do it this way? I'm very confused. So we're squaring it. Yeah, each one is squared. So we have our x term. So we don't have our coefficient term. Which, yeah, it would introduce a bias, right? So we're just saying that it goes through 0. When x is 0, it's 0. Goes through the origin specifically, right? All right, so now we create the model after transforming, right? Well, that's weird. It's not working. Huh. Why? Just run everything again. Oh, I know why. It was supposed to be a difference of 10. That's why. Okay. Let's restart. Let's run all then. That's the difference. That was the reason. This one should only have 5, I think, right? Or 6. 1, 2, 3, 4, 5. 6. So 15, 25, 35, 45, 55 should be 6 of them. There we go. Now it fits. Yeah, that was a mistake there. Polynomial fachas. And then we can get results. It's ready for application. You should keep in mind that the first argument of fit is the modified input array x and not the original x. Okay. So we're going to get results here. And, you know, I was going to save this. I guess I thought that maybe there would be a difference. But it's not like everything is going to be the same, right? Because of the linear nature of this, right? So this is the thing. Wait, no, where'd it go? Results. In the results thing. Let's take this and create a function out of that. So I think what we'll do is up here, or like above here, Um, we're going to define a function, so we're going to like print print model details. We're going to take in a model and an x and a y, right? And so we're going to take a yeah, that's fine. Run that. Go down here and we'll print. Actually, let me just get the outline up here. Really? Okay. But at the very least, like we can go to there and then we can. Multiple step 5. There we go. Step 4 is get results. So what we're going to do is we're going to print model details, and we just take our model, we take our x, and we take our y, and that's what we do, right? Yeah, there we go. And so we get all of that information printed there. Yeah. Bobbity boops. Again, the score returns r squared. Its first argument is also the modified input x underscore not x, so the values of the weights. So it's our transformed values, right? The values of the weights are associated to intercept and coef. So here intercept represents b naught, while coef represents the array that contains b1, b2. Bum bum ba-da-da-da-dump. Ba-dum 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 bum. Beanie beanie. Wait, are we up to that next step yet? No, we're not. So you can do very similar things. Make predictions. So I really think that you should be doing something like this for this. So it should actually go like something like this. Let's just go back to that. Rough likes it that way. It likes it rough. Oh. Right, so you do get similar results there with a 0 intercept and then the coefficient. We get the same slope. Yeah, you get the same, or slope, I should say, the same estimators there. Slope is kind of like, that's a bit of a loosey-goosey way to put that. Probably more likely to say coefficients, right? Yeah, that's what they say. So, that's ERT. Slope is not the right way to go about that, to say that. I wonder if they changed that for the multiple regression. They do say coefficients for that as well. Yeah, I mean, it's the same way with a single variable, but you could call it coefficient, you could call it the slope in that sense. Slope doesn't make sense with multiple values, multiple predictors then. Predict response. Now we'll predict the response. Predict. Not those amateur dicts. Model.predict. X minus there. I mean, so then we could just do that. Predicted response. We're down. So as you can see, picture works always the same way. This requires some modified input instead of the original. Yeah. Several input value variables will work as well. So let's do this. I'm not gonna like cut. Let's see here. All right. When the output off, then you can just copy paste. Okay. By coefficient of determination, intercept is there. Screen test split. We're not going to cover that apparently here. It's really what you should do. Split your data set, but then we're not doing really, this is just contrived stuff, so we're not really dealing with any models here. So let's look at some advanced models here. We're going to import some packages here and probably use them all. Yes. Stats model API is SM. Pretty sure I have stats models. Yeah, we do. I'm just gonna copy this. I don't really want to deal with entering this kind of information. The input and output arrays are created, but the job's not done yet. You need to add the column of ones to the inputs if you want stats models to calculate the intercept. So it's just a function called x equals and do x, so it's just checking it on, okay? And if you show it there, that's what it looks like. Oh, it's interesting. You gotta flip it around. First input is the output. First argument. So you already get the results, which is an instance of the class stats models, regression linear model, regression results wrapper. This object holds a lot of information about the regression model. So, okay, so I guess you get a little bit more. Oh, nice. Look at that. I mean, we don't... It says results summary, but we didn't save the results. Oh, okay. Right. Didn't we do that here? Get results. So you can use the result summary, right? What happens if you do that? Oh, it's just a bound method. Oh, look at that. But if you print this, it's gonna not end up. This is a nicer way to print this. For sure it is. But printing, you can print it to the other one. So let's actually go and do that both ways. Yeah, it depends on how you want to look at this. It's kind of like pretty printed into tables here. But it's monospaced here, so it might be easier to read. Just from a, like, consistency standpoint. It tells you the date that it was run. That's so amazing. Wow, you can just, like, do all your reporting right from there. This is like the output that you would get from, like, a stats software. Like, oh, what is it, like SPS or something like that? Or what's the one? Yes, it's not SPS. What is it? SPSS. SPSS. Stat Graphics RStudio. JMP is a thing of SPSS, isn't it? Or it's of SAS. Which version did I use? I think we used version 11 in our stats class. I wonder if I actually still have those things. Let me see something. Gotta go through. Oh, and before I do that, I want to find out in the media library. That's where I want to find. Projects, right? It was an archive. I don't remember. Oh gosh. Well, I am an archive. Funny enough. Okay, so I'm gonna have to split it from there. Let's go into here. That, and we'll go to. Oh. Okay, I'm gonna add something. A second here. Let me go to. with some quality phrase here. I think it'll be good. So I have to give permission, but that's okay. Back up like this, and then we can do that works. I don't know if it is. I think it needs to reload, but that's okay. It's fine. Okay. What was I looking at? Let me see my notes. Notes and puzzles like device backups or something, maybe. It was in there. Readings, recordings, my data. It's got to be in device backups. Or in education, maybe? Oh, yeah, because I don't know where college. There we go. I think that's here. Oh, gosh. Wow. This would be good to go through. This is definitely something I should. There we go. Stat 330. We use JMP. Oh, I got all my JMP files. I don't have JMP. Wait, were those ones I created? I don't know if those were actually ones I created. Let me take a look at some of these. Here's my first homework. Let's see. Bar graph. Pie chart. Here we go. I didn't write down the questions. Wow, when was this? When was that true? This must have been late aughts. Or mid-aughts. Because by the time late aughts happened, Chrome was probably exceeding that. I would probably change my answer for this, but like I like my reasoning. It's easier to see that one browser makes up the majority. Like just from a glance, you can see that, okay, that one makes more than a half of the pie. But you could also kind of do that with this. If we were to like put a line right on here, that could improve this bar graph. And make it so that you could see the line, like the line of majority, basically. Line of majority market share would be 50%. So I would probably improve that by putting a line at like 50%. I don't know if you can do that with JMP, but like I would do that with whatchamacallit. In the bar chart, it's clear that Firefox has a higher market share than Chrome. In the pie chart, it's difficult to distinguish without the context of their market share percentages shown next to their corresponding slice. I don't hate my reasoning here. This is a really bad PDF, though. Is it like compressed or something? I don't know. How many variables does the dataset contain? Categorical variables, and 3 quantitative. There. Oh, these were fun. Oh, look, you can see the distribution just by plotting the numbers. And then you could see the actual values. So it could be useful for small, right? And then so, but here it's 0.5 is the guide here. 0.5, 1.8, 2.4 GPA. Wait a minute. Stem plot of the distribution of GPA. How is this even real? This can't be right. This is some bad data. GPAs of 7 and 8. Did I just like not... I have no idea what the context is here. I wonder how I created these things. Did I do them by hand? Or as tables? Oh, you can... I must have done it in LaTeX. Shape of the IQ distribution appears to be skewed left. Most of the data is in the 100 to 120 range. No clear outliers. These ones are kind of out there, right? These ones are just outside of that kind of like normal looking distribution here. I would say that these are verging on being that. I don't understand what's going on here. 7, 2, 7, 4. Oh, because it's going from lower to high, lowest to highest. Okay. Yeah. And then the IQR. Oh my goodness, like I don't know why the text looks awful. This font is terrible for this size. But the math font is pretty sweet. Right, this is what I was thinking of when I was thinking of 1.5 times the IQR. It's to test for high outliers and low outliers. So spread could be 66. But the interquartile range is 13 and a half, which would be around there. Oh, these are different data sets. I'm gonna say this is like that's really. I got something wrong there. This is a different problem. Different part of the book. Okay, so we have whisker box plot here. Box and whiskers there. And what is this thing called? Is that the what is that red part? Can't see whether it's unimodal. This would be able to see that you have kind of two modes going on there. 5-number summary for the data. Yeah, there we go. Box plot, made a histogram. This is funny. I just like this. This is really funny. When did we? Because we eventually got to whatchamacallit? The index set. Why did I call it like that? Calculation of standard deviation. That was that. Very simple stuff going on there. Let's see. Let me take a look at my other homeworks and stuff. Oh, I was using licks. That's right. Let me load up all these. That's funny. Study guide to the midterm assignment one. Huh. This might be a good thing to go through. Oh, these are just the... I see. Okay, so this was my... Yeah. I wonder where she is now. I don't know if she's still at Montclair. Oh, maybe she's tenured. Biostats. I wonder what stage of her career she was when. Okay, so she was doing it for like 5 years. Intro stats. She ran a good course, I gotta say. Hard copy. Huh. So weird. Did I try? I think I might have tried to do this in a Oh gosh, come on, dude. What's going on? Did I know? No, I did not know. Yeah, it's so weird. I tried to do it in Word, but But it didn't really work out that well. Here we go. Homework 1 solutions. Oh, these were her solutions. Right. Okay. Yeah, definitely did this in. This is the standard font in Word, right? So, some mixing of stuff there. I did end up changing to a better font. Yeah. Did end up opting for a better font for that. This homework 2. Quantile plot. This is a QQ plot, right? Yeah. It's approximately normal. There's some funky stuff going on down there. Seems approximately normal. And this was randomly generated normal. And there's just some weird stuff going on down there. Yeah, so there could just be weird stuff going on in a tail of QQ plot. If you're like looking in the center of it and there's stuff that's happening, then probably something else is going on. What kind of garbage is this? Yeah. It's not a perfect fit, as evidenced by some bins. The hysterebian overestimates some. Well, of course, like there's always going to be overestimates. What are you talking about, dude? Really, genius. Genius me. Unknown, set it F, set it off. How did I burn out so bad? Oh, look, it's an empty spreadsheet. Fun. Don't know why I needed that. I don't think JMP needs that, right? Oh, what's LibreOffice Draw? That's a weird one. I don't know what that is. Is that like a paint program? Oh, okay. I think this is from mine. I think that's a result of mine. Just surprised I don't have all of the assignments. I don't know why. I don't know why all of the assignments aren't here. I definitely did all of them. Oh, well, okay. Maybe I put them in the folder. That's probably what happened. So some of them are in there, some of them aren't. Word 4 is outside. Mark 3 is here. Mark 2 is outside of that. Okay, yeah, that's what happened. I think I did a better job as the course went on of looking at stuff there. Interesting. You see here. Scatter plot. Yeah, so we factored this by, yeah, so if you looked at the entire data set, it looks like, oh, something's weird going on there. Let's separate it by sex there, when we were still doing such a thing as male versus female. Hopefully they've, included at least some others, although a lot of times they just, get rid of that because, it's just not, even though it's like, I think like, isn't it as much as like 1%, 2%? I guess like just throw away 2% of the data then for non-binaries for NBs. Relationship is strong but not linear. So tiny little print. I don't know why I printed this so tinily. Should have increased the font size. Titanic data. There you go. Huh. I think it was so that I could put like one solution per page. That's very good there. What is that? Base FR. Is that the data set? Oh, I think that was the data set, reference to the data set. But, I don't know. It's weird. It's kind of out of the blue there. I gotta say, I crushed this course. I had already done another whatchamacallit, intro stats course in undergrad, and then I just like took another one that was like a little higher level that at least went a little bit deeper into hypothesis testing. And yeah, I think we like ended with this like very simple hypothesis testing in my undergrad one. Whatever. We're better off anyway, and I don't know if I've ever told you the things that I should say and all that we've lived and died for. We no longer celebrate. And now watch you there through your window, you're crying, your heart is cold like ice, I see you. All right. AIC and BIC is okay. That's listed there. I forget what that is. I think I have that. The Akaiki information criterion and the BIC soon. 2K minus number of model parameters, and then maximize value of the log likelihood. And I like to kick back and think that everything is gonna be okay, but I've walked this road before and it never works out that way. And I'm tired, I'm lost, I'm spent, I quit, I'm fed up with all this bullshit, and I'm leaving. Oh, I wonder if I can do that. I like that. It's good. It's a good pick there. Oopsie. Oopsie dipsy. Most of the BIC, Bayesian information criterion. I don't know. Like, we need to figure out what the log likelihood value is, how you get that. That has to be somewhere. Second look. Ooh. Really? That's the only thing I have. I don't have anything else. Okay. Got these. Table's very comprehensive. Let's get back to this thing here. Get distracted. Actually, let's take a quick break. Alright, so let's finish up here. The comprehensive table, you find them any statistical values associated with the linear regression. Here are coefficients there. Right. And we can print stuff out from here as well. So I'm just gonna copy it. I'm done with today. I'll finish this up. Results. Yeah, so there's many attributes associated with this results object that you get as a consequence of running this model.fit. Yeah. And then notice that you actually instantiate it with the OLS model with the data. R squared holds R squared naturally. The R squared adjusted represents R squared. That is R squared adjusted corrected according to the number of input features. I think that's with the degrees of freedom taken into account, right? DF model 2, DF residuals 5, DF residuals. Yeah, 5 residuals because we had 5 coefficients there for. Weird. Alright, and then so we just gotta go predict the response. And I'm just gonna go ahead and copy the code there. Fitted values and then predict X. That's the same thing. What's the difference? Oh, you can predict it with new data. Okay. So yeah, okay. So it's the same as those obtained with scikit-learn for the same problem. So it's just an alternative way to do the same thing for linear regression, but I'm not sure to what extent stats models, yeah, I don't know how deep it goes. Statistical models, hypothesis tests, and data exploration. So it's not necessarily for machine learning, like whatchamacallit is for. Like scikit-learn is for machine learning. And so like there's just some crossover there, that like classical statistical methods with linear regressions. Like one of the first things that we used to refer to as machine learning. Yeah, so linear regression is sometimes not appropriate, especially for nonlinear models of high complexity. Fortunately, there are other regression techniques suitable for cases where linear regression doesn't work well. Some of them are support vector machines, decision trees, random forest, and neural networks, and there are numerous Python libraries for regression using these techniques. Most of them are free and open source. That's one of the main reasons why Python is among the programming languages for machine learning. Oh, gosh. And then the package scikit-learn provides the means for using other regression techniques. As we've seen, contains classes for support SVMs, support vector machines, decision trees, and random forest. So you can do random forest regression. That's an ensemble model. I'm not sure if I'm going to go as deep into this this time around. If there's a project that calls for it, I will look into it. Basically. Okay. In conclusion, you know what a linear regression is and how you can implement it with Python and 3 open source packages: NumPy, scikit-learn, stats models. Use NumPy for handling arrays. Linear regression is implemented with scikit-learn and stats models. Stats models if you need the advanced statistical parameters of a model. So if you don't need detailed results and want to use the approach consistent with other regression techniques, use scikit-learn, and like for machine learning and stuff like that. But if you want to do like reporting, oh my goodness, the stats model is powerful. Yeah, so that's good to know. In this tutorial, you've learned the following steps for performing linear regression in Python. Import the packages and classes you need, provide data to work with, and eventually do appropriate transformations. Create a regression model and fit it with existing data. Check the results of a model fitting to know whether the data or whether the model is satisfactory, and apply the model for our predictions. And with that, we are good to go. If we have questions, we can please put them in the comment section. Frequently asked questions. What is linear regression and how does it work? Well, I don't know why I can't roll those two R's together. Linear regression. Linear regression. Linear regression. My mouth is, that just feels weird. I don't know. Linear. If I say linear regression, though, it's easier to say because I'm doing the linear regression. I need to like speak with like a speech pathologist or something. Because I don't know. I just have some weird quirks of how my my mouth works here. Linear regression is a statistical method that models the relationship between a dependent variable, one or more independent variables, by fitting a linear equation to the observed data. The simplest form, simple linear regression, involves one independent variable. The method of ordinary least squares is used to determine the best fitting line by minimizing the sum of the squared residuals between the observed and predicted values. Some of the squared residuals we could have like fleshed out here. I think we have that up here, don't we? Right here. Yeah. Some of the squared residuals right there. Using the method of that. So what we can do is take that. Where'd it go? There it is. There we go. Some of the squared residuals right there. Okay, can you implement linear regression in Python? Well, yeah, okay, so what's the difference between simple and multiple linear regression? Well, it's the number of independent variables. Basically, simple means that there's only one single independent variable, and multiple linear regression is that there are more than one independent variables. And so to use scikit-learn, you import the libraries, you instantiate the model, right? You create a model. Well, you provide you get the data into some NumPy arrays, and you feed that data, and then you create a model, and then you fit that data to the model, and then you run. You get results from that, and then you make predictions. It's obtain the model parameters, so that's getting the results. Model parameters were coefs and intercepts. And the prediction. So what's the formula for linear regression? How does that work? Yeah, okay. I don't really want to talk about it. That's too much detail. Too much detail right now. Okay. This is a decent little article here. Oh, I think let's take a look at some of these. Very nice article. These tools are lousy. Statistician and R is so much better suited to running simple statistical models. The formatting requirements of the data to apply that Fourier Python routines are a bit weird too. Wow. Okay, John. Okay, John S. Why did they make it so awkward compared to R? I don't know what he's talking about here. Formatting requirements of the data? You're talking about putting it into NumPy arrays? Is that too hard for you, John? I don't know. Jeez. Why'd they make it so difficult? So awkward. It's just because they didn't. It's scikit-learn is really like what version are we on? We're on 1.6. Oh, actually we are. Okay, so we are up to 1.6. I remember when it, because 1.1, that was like not too long ago, wasn't it? Let me take a look at the changelog and stuff. Roadmap there, other versions and download. Scikit-learn in 2018. So much has changed. I think, was I on 1.1? I could have sworn we were still in like this zone when in like 2018. Yeah, look at this. I'm in April 2021 and we're still in beta. I'm actually surprised. I think there is some better ways to, I don't know, like, I think it might be a little bit easier to, wow, they really just like churned up production of version 1 of development, I should say. Oh, there's release history. Let me go back there. Great. Yeah, okay. Unstable development version. Okay, so let's switch to the stable one. Okay, so the look up linear models. Yeah, they don't have to be NumPy arrays anymore. I think you can take in some other stuff. Linear regression. They don't necessarily have to be NumPy arrays. I think they handled a lot of different types of inputs. Although it's just standard to use the NumPy arrays there. I do think that you can take in, let me see, where's the data? It's array-like sparse matrix of shape and samples and features. Array-like is doing a lot of heavy lifting there, because I think you can add in like pandas arrays or pandas series into that as well for the X and or for your data for your usually what you're going to be doing is to be working with like pandas data frames and stuff like that, right? So I mean, that's why, John, that these simple statistical models are a little awkward because this is simplified. I feel like I have to come to the defense of this. This tutorial is only focused on linear regression. It's not focused on pandas. What you would usually be doing is using pandas data frames. And I think you could pass in pandas data frames as your X for the training data. And you can also pass in a series for Y for your target values. If I remember correctly, that's what we did at Lambda School. Yeah, so I'm gonna I have to bow out now. It is it's time for me to put an end to this day. So we fleshed out the linear regression note, added a lot to this one. Brought in some related notes, defined some terms here: coefficient of determination, sum of squared residuals, underfitting, overfit. Ooh. Yeah. Linear regression is a statistical method for modeling the relationship between a dependent variable and one or more independent variables by fitting a linear equation. Okay. So, yeah, I had like some of the math, and I think this was from doing data sciences where I pulled this from, or I just like, I don't know where. I had like a note. Oh, I think I had like a card or something, an index card. Yeah, I don't know where I pulled that formulation from. All these like betas or the gammas. Why is it gamma? Gamma XY. What is gamma XY? The sample correlation coefficient. Yeah, I don't remember what the heck that was. Correlation coefficient. That's something I need to check on. Coefficient of variation. We didn't really go into that. The standard deviation divided by the mean. Is that what that is? And then the sample standard deviation divided by x bar. Yeah. Compare CVs to determine which has more variability. Is that between samples, between populations, I guess, or subpopulations? Okay, fleshed out rectangular data. Did we do anything with that? I don't know what we did with this. Oh, we were just looking at more of the outcome and output, target, response, dependent variable. That's where we were looking at that. Yeah, because, yeah, we were just looking at features, independent variables, features that. So we can actually, independent variable is what we could call for that. We just added a little bit there. All right, so that's it. Takeaways for today. What are the takeaways? My brain is chaotic. that should be a takeaway. Takeaway should be that it's not been a great week. Been very distractible, and yeah. Well, for today. Yeah. I don't know. My brain's kind of mushy, so I'm gonna just end it here for today, and so be back tomorrow. Going into let me see, the well-grounded. The well-grounded data analyst. Can't remember which projects were which, so we have to look at the let me see. Here. Actually, before I do something, I want to add a hotkey here for switching to an annotator. Let's see. Alt-Shift-A? Does that work? I know Control-Shift-A would be select all, right? And then like... Wait, what is Control-Shift-A? Does that work? Control-A is select all. Control-Shift-A. Oh, well that's because it's a other thing. Okay, I think that's what I want from there. So what I would like to do is just go here into I think it was here. This is like so... Huh. Let's hit it. Oh. Okay, whatever. Why is this like that? Page width. I guess we would just do page width. This song is by Fallen from Grace. Okay, so chapter 4 is separate. That's with metrics. So we'll skip data modeling for now, and I'll come back to it at another time. We'll go into metrics tomorrow, and then go into the analyzing the effects of that with unusual data sources, right? Yeah, okay. So that's what I want to do. J. Broadnax. That's an interesting name, isn't it? Okay, so yeah, that's it there. What's power show? Poetry show. Yeah, I don't like using poetry. Package and dependency management system. Yeah, virtual env. The problem with like virtual env is that you have to keep updating it. I like that the idea with UV is to just like add a dependency and it creates the requirements text for you, which is like that's where it should be. I shouldn't have to like do everything, you know, because I'm gonna forget all that stuff. But anyway, okay. So tomorrow, do metrics of that book, and then holding off on the data modeling that I did a bit of yesterday, or I didn't even start the project. So I'll do that project at another time. And this weekend I'm gonna have to edit some of the videos, or the descriptions and the thumbnails and those things. So, yeah, but day by day, we learned a bit of linear regression here today. And just remember, folks, we are one day closer to Donald Trump not being in office.